two types of diffraction called as Fraunhofer and Fresnel diffraction. Fraunhofer and Fresnel diffraction. So what do you mean by Fraunhofer? So here I'll take a source of light, then I'll take the converging lens. I'll keep the lens in the focal plane of the, I'll keep the object in the focal plane of the lens. Are you able to understand? So this is the focus. I'll keep the source in the focal plane of the lens. Then the rays emitted by the light will be incident on the lens. After refraction, they'll become parallel. So how this slit, this gap is a slit. So the slit is illuminated like a by parallel beam of light. So this parallel beam of light means as if the source, as if the light is coming from infinity. Because all the wavefronts will be vertical. So this is as if the slit is illuminated by a source which is kept infinity. The meaning of that one. Then here the bending of ray of light occurs. Again, to obtain the pattern on the screen, I'll use one more converging lens to get the well-defined the pattern. So two converging lens will be used here. So in this case, the source of light and screen are at infinite distance. But sir, we are seeing at finite. No, don't bother this. Actually, this is a source of light. For the slit, what will happen? This parallel beam of light will become like a source because they're coming from almost like infinity. Similarly, same thing here. After refraction, parallel beam of light, I will focus it on the screen by using this lens. So what is the duty of this lens? Here, it will produce a parallel beam of light. Here, the parallel beam of light which is there will be converged at a point. So this lens, the duty of this lens is to only for focusing purpose. So in fact, this is like a source at infinity and the screen is at infinity. Okay, this is what Fraunhofer diffraction. Then in Fresnel diffraction, we don't use any lens. Source is at finite distance. The screen is at finite distance, but here also screen is there. So after focusing the rays by a lens, what happens? The light will be incident on the screen. If this lens were not there, so this particular parallel beam of light will illuminate the screen. You keep the screen even at infinity. So this light will go and incident on screen. So as good as like the screen at infinity. There's a terminology here. So here both are at finite distance. So we don't use any lens. The mathematics involved will be very complicated. The maths involved will be very, very complicated. The source and the screen will be at finite distance. Okay, let's compare them. In the Fraunhofer and Fresnel diffraction, source and screen are at infinite distance from slit. Okay, this what here. Then incident wavefront on the aperture is plane. You can see that one. What is the wavefront? Here it will be plane wavefront will come. How the wavefront will be? The wavefront will come like this. Unable to show it. Or I'll show. So the wavefront will be like this. Plane wavefront. And after diffraction, again the wavefront will be plane. Incident wavefront of aperture is plane. The diffracted wavefront is also a plane. Okay, the incident wavefront is a plane. What about the diffracted wavefront? It is also a plane. Able to get this? It's also a plane. Then two converging lenses or biconvex lenses are used to study diffraction pattern in the laboratory. Mathematics will be very easy. That I'll show in the next coming class. Later, I'll show that. Then it has many applications in designing optical instruments. So what all we have, telescope, microscope, no, or the cameras or the television, what all we have, the viewing objects, the digital screen, what you're seeing, no, all they are based on this particular, the Fraunhofer diffraction. And the maximas, minimas, which are formed are well defined. Minima as zero intensity, maximum intensity. I'm able to see very clearly, I'm able to notice the maximas, minimas. This one, well-defined maximas, minimas. Here you can see that one, no light, maximum light, again, no light, maximum light. So maximas and minimas are well-defined. Let's come for Fresnel diffraction. The pattern will be like this, the first. So what about here? Though it's a minima, still it's having light. So how the pattern, this will be more light, this will be lesser light. So it'll be very difficult for us to really identify what is maximum minima. Here see no light, that will be minima. Maximum light, S maxima. Here no light, completely dark. Here open complete dark will not be there. So some light will be there. Are you able to notice? Non-zero intensity. Suppose here 10 watt, here 2 watt. Is it also 10 watt and 4 watt? Can you really identify the lab? This is a minima because here 10 watt, 10, 8, 6, 5, 4, 3. So 10, it will be like a 8, 6, 4. Again, what happened? 5, say some 6, it will become. So this intensity 4 watt and this 10 watt, very difficult to differentiate in the lab. So almost what you can say that complete dark region not available. So well-defined pattern what happened means very difficult to identify the bright and dark bands. That is the one drawback of this particular thing, Fresnel diffraction. Okay, now source and skin are at finite distance from the slit. Incident wavefront. So if you come like this, the wavefront will be cylindrical. The wavefront will be cylindrical. No lenses are required like what we use in the Fraunhofer. Mass involved will be very complicated because the intensity is not non-zero at these points, and very less applications what we use. And the maximas, minimas are not well defined. I'm unable to define this minima. I can't say in a lab, I'm unable to say which is maxima minima, to be frank. Suppose you have a light of intensity 10 watt and 6 watt. Both are beside. So it's not possible for you to really identify the 10 watt and 6 watt region. The means there are two regions are there, 10 watt and 6 watt. You can never say that. Means a good example, I'll give it. Okay, there's a thing. I'll show by other colors. Intensity of this is more, here it's less, but not zero. If it were like this, it would have been no light. You can say no light. Completely dark. Okay, there's again. Okay, there's a white band. I'll put it here. No. White band, dark band. Okay, the intensity is varying. So if the pattern is like this, the 194, I think there won't be any problem for you in identifying. But the 2 and 3, if the pattern is like a 2 and 3, very difficult to identify the bright and dark, no? If this pattern is like a 194, made up of 194, and I'll better draw it beside it. Okay, let me set right. Yeah. Anybody will easily say that 192, okay, 3 and 4. So tell me like here, bright band, dark band. What about here? Difficult, no? Like to distinguish actually bright and dark. This is what happens in this case. Here, what happened? It will be like